Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 23 in the course Advanced Robotics. In the last class we looked at the control of a single joint, and we said that the basic way the manipulator is controlled is that we are making the assumption that this is independent joint control. That means every joint is independently controlled, and every joint has an actuator, which is a motor, then there is an encoder, which is the position sensor, and there is a gear in front. And in the last class I also emphasized that in reality this is a nonlinear control system, okay, but we are approximating this with a linear control theory. So from there we'll proceed today, and we'll see how to design PD controllers and PID controllers for control of for independent joint control of single joints of a manipulator. Okay, so in the last class we talked about control of a single joint, and I'll just very quickly revise what we had talked about in the last class. We said that every joint is actuated. So we have joints here, and every joint is actuated by a motor, and there's a gear in front, and there's an encoder at the back. Okay, and I also said that in reality this is a nonlinear control system, but we get away by doing linear control theory essentially because there is a gear in front, and any change in the disturbance when a robot picks up an object or drops an object, that gets minimized because the effective inertia, when you look at it, so it is Jm by Jl by zeta squared into theta m double dot, right? Now, because of which we see that the effect of the change in inertia when a robot picks up an object or drops an object is minimized, and due to which this type of linear control system still functions. Okay, so today we'll see this further and look at the design of a PD control and a PID controller. So let's revise very quickly with what we were doing in the last class. So what we saw in the last class is that I'm revising very quickly what was done in the last class. So we have a manipulator like this, and there is a motor, gear, and an encoder at the back, and we give voltage to the motor. The motor rotates, because of which the joint changes, and the joint change means the end effector position also changes. Okay, now so there is one input, which is the voltage, which is coming here as the reference trajectory. We are giving the reference trajectory that we want the manipulator to follow. That is one input. The second input is the dynamics, the tau m theta double dot plus v plus c theta. What is this doing? This is causing a disturbance. So this is coming like this, and this is tau. This is a disturbance, and that my tau is coming here as a disturbance. So basically we are seeing that this is a two input system. Okay, so there is one reference which is required, that is my desired position, okay, in terms of the end effector or in terms of the joint angle, and there is an output which is my theta m position of the motor, and there is a disturbance which is coming, which is the dynamics of the system. So what does this basically mean? This means that if I'm trying to move in this direction, what the dynamics will do is it will try and oppose that motion. Okay, or suppose one joint is moving, this joint is moving like that, okay, and these two joints are not moving. So this joint is not moving, this is not moving, but just because theta 1 dot is there and theta 1 double dot is there, this will be subjected to forces and moments. So that is a disturbance on the controller, because the controller understands that the joint is not moving, right? It's holding the position at that angle, and yet it requires additional torque because this disturbance is coming from the first joint, which is disturbing the second and the third joints. That is the meaning of what this does. Okay, now so we have input, which is my reference trajectory. We have a compensator, so this we can call it a controller. Okay, what it does, controller gives an output which is passed through a power amplifier. Basically we increase the current, and then there is a summing block here which takes the disturbance. Then this is my plant, this is my robot link. Okay, so this is my robot link, which can be the motor which is actuating the joint. Then there is an output, and there is a feedback which is coming, and this is my position sensor which is going back. So this is the basic structure of my independent joint control of a single joint. Okay, so the control of a single joint has this structure. It's a feedback control system. Now, couple of things to note. Number one is that it has two inputs now. One input here, another input there. Okay, and what are we trying to control? We're trying to control a motor. So let's look at the actuator dynamics, and we understand that this is a motor and how it basically works. We understand the working of a DC motor. There is a rotor inside. So this is my rotor, and this is the stator, which is outside. The stator is a permanent magnet, and there are magnetic lines of force which are moving, that as shown. Now when you pass a voltage through this this rotor, what happens is it generates a magnetic field. Now that magnetic field interacts with the magnetic field of the stator, and there is a resultant moment on the axis of the rotor, because of which it rotates. Okay, now the torque that is produced by the motor is equal to Ki into phi. Phi is the magnetic flux density, Ia is the armature current, and this can be written as tau m is the motor torque, which is equal to Km into the motor constant into Ia, which is the armature current. Okay, so this is one equation that we have. Now when this is rotating, what happens is there is a voltage in the coil. Okay, so this voltage in the coil, if I draw it something like this, okay, let me draw the construction of the motor. There is the coil inside here. So that's my coil. If you can imagine, there's a plus minus, and this is this is the other side. There is another magnet here, like this. Okay, so this is my north, this is my south. So this is rotating about this axis like that, and this is carrying a current. So what is happening is there is a conductor which is moving in a magnetic field, okay, which will ensure that there is an EMF induced in that conductor. Okay, and this EMF is called the back EMF. So there are two voltages. One voltage is the voltage I'm giving input here. I can call it V in. And because this conductor is rotating in a magnetic field, what is going to happen is there is going to be an EMF which is induced in the conductor, which is going to oppose this V in. And that is called the V back, which is VB. Now the V back is equal to K back, or rather let's call it K2 into phi into W into M, omega into M. So the back EMF is proportional to the angular velocity at which the motor is rotating. So VB is equal to KB into d theta m by dt. Okay, so this is the second equation. Okay, so we have the amount of torque being generated by the motor, which is proportional to the armature current. The second is the back EMF, which is being induced in the conductor because it is rotating in a magnetic field. Okay, now let us proceed further. Look at the circuit diagram of the rotor. Okay, so this is the rotor which is rotating. There is the coils in the rotor. So this is my coil, and inside in the coil we are giving a voltage, which is my voltage in. So this is V in. We can call this V in. This is the voltage I'm giving to the motor. There's a V back which is being generated here. That's my VB or V back. So the total voltage in the system is equal to V in minus V back. Okay, in the armature. Now in the armature there are coils, right? So there's an inductance and a resistance. So there is an inductance and there is a resistance in the coil, and there is a current which is flowing, which is IA. So if I use Kirchhoff's law, basically what we get is L di by dt plus R of IA is equal to V minus VB. Okay, so here it becomes L di by dt, and here it is R into IA, and the effective voltage is V minus VB. Okay, so this is one equation that I have. So let us write down one equation which is for the, so let's call this equation 1, which is for the armature. Now if you look at the physical model of the connection. So if I draw my connection here like this. Okay, so this is my link. In the link there is a motor, there's a gear sitting, and there's an encoder. Okay, for every joint. So on one side we have the motor. So the motor, there is a Jm, which is the inertia of the motor. This motor is connected to a gear, which is shown here. So that's my gear. So let's say that this is my gear, which is connected here, and and the output of the gear is connected to a link, and let me say this is the inertia of the link. Let me say that this is JL. Now when the motor rotates, it produces a torque tau m, and there is a angle theta m. This is tau L and theta L, and this is my gear ratio R. R is the gear ratio, and there is damping, which is Bm on this side and Bl on this side. Okay. Now if you look at the torque balance here, the equation of motion of the system is then, if we start looking at the torque balance, it becomes Jm into theta squared, d squared. So this is Jm into theta double dot, theta m double dot, plus Bm into theta m dot, which is equal to tau m minus tau L by R. Okay. So that is the equation that we are getting from here. So the torque being produced by the motor is overcoming the friction and is equal to the motor torque, and the motor torque is getting reduced or being consumed by the load side. Okay, so this is my other equation. This is same as this one. Now in the previous equation we saw that tau m, what was tau m? Tau m was equal to here. Tau m was equal to Km into Ia. Okay, so what we do is I replace this tau m by tau m was equal to Km into Ia, armature current. So from here what we do is I get this equation. Okay, so what I'm going to get is Jm theta m double dot plus Bm into theta m dot is equal to tau m. So tau m was equal to Km into Ia minus tau L by R. Okay, now this is my other important equation. Okay, this gives me the torque balance equation. So one was an equation of the armature. The second is the motor and the link, actually the torque that is being generated by the motor, which is being consumed by which is being used to rotate the link. Okay, now taking the Laplace transform of the first equation. So I take the Laplace transform of this equation. So what do I get? So I get L, I get 1s I plus R into Is, which is equal to Vs minus Vbs. This can be Vm, we can call it, or this is the voltage in, or Vi. Okay, so this is what we get. So this is my first equation that I'm getting. Ls plus R into Ia is equal to V. This is the first equation I'm getting. And what we have done is we have put the back EMF in there. So Vb, if you notice, Vb, what was Vb equal to? V back is equal to Kb into theta m dot. Okay. So if I take my Laplace transform of this, what will I get? S into, so if I take my Laplace transform, I'll be getting Kb into S into theta ms. Okay, so let me write it down. So this was equal to Vb is equal to Vb into S. So I can write this as V of S, and Vb into S I can write as Kb into S. So Vb is equal to Kb into theta m dot. So Kbs theta ms. Okay, that is what I'm getting here. So this is one equation that I get. So let's call this equation 2. Let's call this equation 3. And if I take the Laplace transform of this one, I get equation 4. Okay, so Laplace transform of this would be Jm theta m double dot will become Jm s squared plus Bms into theta ms, and the other side I get Km. So this is Km into Ia minus tau L by R into S. Okay, so I have these two equations. Okay, so we see that we have two equations now, and these two equations are giving us what? These two equations are giving us two inputs actually. Okay, this is giving us two input system. What are the inputs? One is the Vs that is coming, okay, the voltage in that is coming. The other is the tau L, which is the disturbance. Okay, so this is a two input system which is coming now. Now let's draw the control system of this, and what would it look like? Let me go back and explain how do we get this. So here what you get is, let's look at this. So what we are getting is Ia is the armature current. Okay, so this is my input Vs. Vs is getting multiplied by 1 by Ls plus R, which is giving us IAS. And where did that come from? So if you look at this equation, Vs is coming in. Okay, so what is, if I take this equation, IAS is equal to Vs minus KBS into theta ms, okay, divided by Ls plus R. Okay, so this 1 by Ls plus R is coming and Vs is coming here. So Vs minus Kb into S is on the top, and in the denominator it is Ls plus R. So if you look at the control system, so Vb is coming from here. Okay, so Vb is coming from here. So in this, what is happening is it is Vs minus Kb into, so this top term is coming there. So Vs minus Kb into S, theta ms is coming from there. Okay, so theta ms is coming from here. Okay, and then that is the denominator, and in the numerator you have, sorry, on the denominator what do we have? We have Ls plus R, which is here. So on the denominator you have Ls plus R. So when Vs minus this, so this minus this is getting multiplied by this block, and what you're getting is IAS. Okay, now I hope you understand how did this block diagram come from this equation. Okay, so IS is equal to this now. Similarly, we have the other input, which is tau L. Okay, so where is that fellow coming from? So tau L is coming from here, which is my disturbance. That is getting multiplied by 1 by JMS. Okay, so 1 by JMS is coming in the so here, let me wipe this off. So what is theta ms? Theta ms is equal to, so from this equation, theta ms is equal to K into IAS minus tau L by RS divided by JMS squared plus BMS. Okay, so I can take one S out and I make it 1 by S, so this becomes JMS plus BM. Okay, so that is equal to theta ms. So if you look here, theta ms is here, so theta ms is equal to K into IAS minus, so IAS into Ki, that is coming from here. So this IA will get multiplied with this minus tau L by R. Okay, it will be divided by JMS plus BM. Okay, and this is coming, and there is a 1 by S there, and this is my theta ms. Okay, so from the second equation we get theta ms, which is here, and this is how we get our block diagram of combining both the equations. Okay, so this is my block diagram for a 2-input system. One is my input here, that's one input. Second input is that one, which is my second input. Okay, now I need to find the transfer function for this. Now, why do we need the transfer function? Because we need to talk about stability of the system. In order to get the stability, I have to convert this into the form an input-output system. This is my transfer function. This is my input, that's my output. So this is my in, that's out. So I basically need I by, okay, IS, OS by IS, which is my transfer function. Then I need to look at the denominator of the transfer function, which is my characteristic equation. Look at the poles of that, or look at the roots of that, and then see whether the system is stable or unstable or not stable. So in the last class, I had discussed about how to find the transfer function, or how to convert the various blocks and into this type, okay, into an input-output system in case where there are 2 input systems. So in the case of a 2-input system like this, we use superposition. Now what superposition is, basically we say find the transfer function assuming that tau L is equal to 0, and add with the transfer function, okay, this is what, let's say 1, this is 2, with the transfer function assuming Vs is equal to 0. So in one transfer function we assume this to be equal to 0. So if I put that equal to 0, this is not there anymore. Okay, this part is not there. Okay, so basically I just multiply all these blocks together. Okay, and then it's a GS by HS. So please refer to the previous lecture. So this is my GS by HS kind of. So it will become GS plus 1 plus GSHS. Okay, this is what it will come finally. Okay, so we have GS, combined GS on top and HS at the bottom. So if I combine it, this is what it will come to, and this is going to be my characteristic equation, okay, of that particular transfer function. Okay, so now what we do is, for the first case, I'm assuming tau L is equal to 0. If I say tau L is equal to 0, then my output is theta ms and my input is Vs, which is this one. So this is one transfer function TF1. And if I simplify it, I get my transfer function like this. Please simplify it. This is what we'll get. Okay. Now my transfer function 2 is by assuming Vs is equal to 0. So if Vs is equal to 0, then my transfer function is, this fellow becomes equal to 0. Okay, this side is not there. But please note there is a minus sign there. So this will become minus. Okay, minus 1 by Ls plus R, because there is a minus sign there. This is equal to 0. So that my input is this one, now this is my input, and output is theta ms. So output is theta ms and input is tau ls, and my transfer function comes out like this. Okay, so by superposition, what are we doing? We are once assuming that one of the input is 0, then the second time we are assuming that the other input is 0, finding the transfer functions, and then we'll add them. Okay, that becomes the combined transfer function. Okay, so next is we did find the two transfer functions. Now what we do find is that there are terms like L, which is the inductance, R is the resistance. Okay, now for a motor we know that the electrical time constant L by R is as good as 0, is almost equal to 0. So what we can do in the previous equation, in this equation, so L by R we know is equal to 0 or very equal to 0. So I divide this by R, so I get L by R here and I get 1 here. Okay, so I divide this by R. Okay, so when I divide this by R, what I get, and I set L by R equal to 0. So what we are doing is putting L by R equal to 0. And if I do that, what would happen is, because there is an L by R here, this will become 0. This is 1. So what will be left with is only this. Okay, and that is what I'm left with. And there is an R, because I divided by R, there's an R there. Okay, so what we did is we set L by R equal to 0 in both the equations, and we reduced the number of terms. So you see that some terms will become 0. And now my transfer function is theta m by v, theta ms by vs is this, and theta ms by tau L is this. Okay, so these are two transfer functions. This transfer function we got by assuming tau L equal to 0, and this transfer function I got by assuming v is equal to 0, vs is equal to 0. Okay, so I have two transfer functions now. Now when we combine them, so this is in the S domain, this is in S domain. So if I convert it into time domain, from S domain I come back to time domain. Okay, my equation will be this. Okay, so there are two inputs. One input is this one, and the other output is another input is this one. Okay. Now if I write the block diagram exactly the same way which we did, as I just explained some time back, that there is one input Vs here and there is another input there. Okay, and if you look at this equation, what is happening is there is Im which is coming from here. That's my Im. So it is Vs minus Kb into theta ms. Okay, and that is becoming my Im. Okay, and that Im is getting multiplied by Ki by R, which is here, and there is a minus. So whatever is going from here, there is a minus tau L by R, which is this one. So please look at this equation and try to understand what this equation actually means. So take a bit of time to actually understand what this equation actually means. Okay, so what you have seen is try to correlate how did we come from here to here. I had just explained two equations when we drew the, so I had explained this equation and this equation. Using these two equations, how did we come to this block diagram? Now, exactly using the same procedure, we have one equation. This is in the time domain which contains both. Okay, so we are getting this block diagram, okay, which has two inputs. One input is Vs, the other input is tau L. Now, what I need to do is we need to now add a controller. Now let's look at this and understand this equation properly before we proceed any further. Okay, before I proceed any further, let me look at this equation properly. Now look at this equation properly. Okay, you have looked at the control system, the block diagram. Now please look at this equation properly. Now there is one input here. There is my input here. Okay, that's the voltage to the motor. Okay, and there is another fellow here who is the dynamic torque. This is because of dynamics. Okay, these are two. So when we say design a control, and this is my motor. Okay, so this is my motor. I can simplify this and make it Vm. Let's simplify this and call it Bm. This is Jm is the motor inertia. So motor inertia into motor acceleration, motor damping into motor velocity is equal to the voltage that is being given input into the motor into the motor constant Km minus the dynamic torque tau L. Okay, so when we are saying design a controller, what the controller will be doing, what is the controller doing? The controller is going to decide how much voltage is going to go to the motor. Let's go back a little bit and try and understand this. When I'm saying controller design, okay, well, let me come here. What is the controller actually doing in this? Controller is designing this one. Okay, so controller is deciding how much voltage should go to the motor to get the motor to a desired position. Okay, so if I go back even a little bit more, so this is my controller here. This is my reference trajectory. This is my controller. So what is the controller doing? The controller is deciding how much voltage output to give to the motor. Okay, so if it's a PD control or a PID controller, your controller is sitting here now. That's your controller. Okay, and that is the one that is deciding how much voltage is going to go in. So in this equation, the input here is my controller. This will be decided by the PD controller or a PID controller. We'll start off with PD, then we'll go to PID. Okay, what is the dynamics doing? The dynamics is going to oppose. So dynamics is going to oppose as a disturbance. So this is my disturbance. Okay, so when we are saying controller, I need to design or I need to frame a controller. If it's a PD, it only has a KP and a KD, and I'm going to put it here. That is going to decide how much voltage will go to the motor. If it's a PID, then it will be a KP, KI, and KD. Okay, so the next thing that we need to do is I am simplifying this equation as I just wrote. So these full terms are being simplified by one term Bm, and I'm writing my equation like this. Okay, so it is J effective into theta m double dot plus B effective into theta m is equal to K into Vk. This is my input, and minus R into dk. Dk, what is dk? Dk is the dynamic torque. Okay, so dk is the dynamic torque, which is this one now. That is the dynamic torque, okay, which is equal to d into theta double dot plus c into theta dot plus g into theta is equal to tau, and this tau is actually there. So actually, if I write my full equation, okay, my full equation is going to become what? This equation, if I write it fully, this equation is basically equal to, let me write it here, J effective theta m double dot plus B effective theta m dot, okay, is equal to K into Vk. Now this Vk can be a PD controller or it can be a PID controller, minus R into dk, R into tau L. What is tau L? Tau L is equal to d theta double dot plus c theta dot plus g theta into gear ratio R. Okay, so this is my total equation actually. So what you understand is this is the motor side, that is the link inertia, and this is my controller now. Okay, that is the full system which we are trying to control. Okay, so in short, we are writing it this way. And what I'm basically going to do is I will design a controller and I'm going to make the controller and put it here. Okay, that is going to be my controller. But please remember this equation because we'll be coming back to this equation repeatedly. Let's call this equation A. Okay, so when I decide a controller, I will design the controller, put it in Vk, then look at the transfer function, look at the characteristic equation, and then try and see whether the poles are on the left side, the right side, how it is. So first of all, we decide a PD compensator or PD controller. Okay, now this PD controller has a KP and a KD. This is something we have studied. So it's a proportional gain and a derivative gain. So KP into theta ds minus theta ms. Theta ms is the present position of the motor. Theta d is the desired position of the motor. And yeah, so this is my, so I take this Vk or V in and I put it inside the previous equation. Okay, so let me look at the previous equation. What was the equation that we wrote? And we put it inside that one. So that is the B effective versus my equation was J effective into theta m double dot plus B effective into theta m dot would be equal to K into Vk. In this case, it is Vk plus minus r into dk. Okay. Now if it's a reducing gearbox or it's an increasing gearbox, it can be r into dk or dk by r. Okay, what did we write? A couple of just have a look to have conformity what we are writing. So it is tau L by r. Okay, so we can simply write it as tau L by r in all cases. So where is that equation gone? So it is this will become dk by r. Okay, by r. So here also it becomes dk by r. Okay, now so I'm taking this and putting it here now. So what do we get? So let me write the equation again. It's not very difficult once you understand, but there are a lot of terms. Effective into theta m double dot plus b effective theta m dot is equal to k into my vk is equal to kp into theta ds. Oh, this is in S domain, so I need to convert to S domain. So let me just convert to S domain. S squared theta ms into S into theta ms. Okay, yeah, minus theta ms minus kd kd into S theta ms minus dk by r. Okay, so this was my equation. I put my controller here now. So when we say design a controller, you actually make the controller and put it in here. Now we have theta ms. You can see theta ms is there and theta d is there. Theta d is desired. This is my desired position I want to go to. Theta ms is the present motor position. Okay. So now what I do is I bring all the theta ms and the theta ds on one side. So there is theta ms. I take it on this side. So on the right hand side you only have theta ds. Okay, and you have this term dk by r. So on the right hand side we only have two terms left, which is going to be this is one term and that is going to be another term which will be on the right hand side, and theta ms will go on the left, theta ms will go on the left, and then I take theta ms common. So I take theta ms common, so this is actually by omega s, and the right hand side what you get is k into kp theta d s, okay, minus d, this is my let's call it ds by r. Okay, this is what I get. So this will be a theta ms and all kinds of terms will be inside here. Okay, so I hope you understand what I did. I took all the theta ms on the left hand side. So on the right hand side we are only left with theta ds and the other term is dk, that's the dynamic torque by r. Okay, and so now when I take theta ms, what will happen, this omega s will come in the denominator. So this will become by omega, this will become by omega, which is this equation now. So it is this equation now. So theta ms is equal to kkp by omega s into theta ds minus 1 by omega s into ds, and there is an r there. Okay, so now this is my transfer function. Now if you look at the denominator of this, the characteristic equation is omega. Okay, so this is my characteristic equation now. So my characteristic equation is this. Now if you look very closely, this is similar to ms squared plus bs plus k. Remember this equation of the spring mass damper. So we had a spring mass damper, mass, spring and damper. Okay, and so mbk system, and this mx double dot plus px dot plus kx was equal to 0. If I take the Laplace transform, it is this. It comes exactly in this way, almost similar to this. I mean the form is the same, it's square. Okay, so ms squared, this is j, which is inertia into s squared. Now the question comes, is this a stable system? Now in the case of this, we talked about Lyapunov stability and I showed that this is a stable system. It cannot become unstable. Why? Because the roots are negative. Okay, so roots are negative. Okay, on the left of the j omega axis, always. Why? Because m, b and s are all positive. So m, b and k are positive. M, b and k are positive. Hence roots are always on negative, hence system is stable. We also used Lyapunov theory where we derived a Lyapunov function. We took its derivative and then we showed that this is a stable system. Okay, so a PD controller or a PD compensator is always stable. Okay, it cannot become unstable. Okay, and hence it is used, always used in a system. It is the most common type of control system used because it is always stable. It can never become unstable. Now let's look at we need to look at another term which is called the error steady state. Okay, the error steady state, or ESS, is the error that is going to remain when time goes to infinity. So when we talked about the response of a system, if you remember that I've been drawing this graph for a spring mass damper system. This is my mass, this is spring, and that's my damper. And I said that if you give a disturbance F and you leave it, what will it do? It will start oscillate, depending on the values of M, B, and K. Okay, it will either oscillate, so it is underdamped, overdamped, or critically damped. It will behave in a particular way. So it will come like this. So it will come, suppose I take it to the point X and I leave it, so this time, okay, that's my X. It will either come like this, or it will come like this, or it will do like this. Okay, but the question is, as time is going to infinity, what will happen here? What is happening there? That is my error steady state. As time goes to infinity, will it actually go and meet zero again, or it is never going to meet zero again? Okay, so as time goes to infinity, what is the error? And that we need to examine that, because this actually means that the system will never reach where you desire it to go. So my desired input was theta d. Okay, will it ever reach? So will it ever reach theta d? That's the question, because here it is showing that there is some gap there. So the way I have drawn the graph, you can see that there is some gap there. So that gap is my ESS. Okay, means this is whatever you do, irrespective of what you do, it is never going to reach. There will be some small error. So how much is that small error? We want to know. How do we find that? Now the error is equal to, so error E is equal to theta d desired minus theta m. This we have seen when we talked about our position regulator controller also. So theta d minus theta ms. Now you know what is theta ms. What is theta ms? Theta ms is this. So this is my theta ms. So I have theta ms equal to this. So kkp by omega s into theta ds. So I take my theta ms and put it inside here. Okay. After I do that, then I take theta ds out. So what we get is theta ds. Okay. So theta ds and omega s comes at the denominator, and there is a theta ds into 1 by omega s by ds by r. There is an r there. Okay. So what did I do? I took my theta ms. Where did I get that from? I got it from the previous one here. I got theta ms here. So I put that theta ms, take theta ds common. Okay, so this is theta d common, and what we get is ES is here. Okay, so omega s is at the bottom. This is my characteristic equation. Now for a step reference input, suppose I give a step function. This is my step function. I give a step reference input, omega theta d by s. Okay, is my step input, and there is a constant disturbance. Please note that I'm assuming that my dynamic torque, which is coming tau, which is equal to theta double dot plus all those terms. Okay, this is actually time varying disturbance. Okay, but we are making the assumption that it's a constant disturbance, and I simply say that it's a constant disturbance. Tau is equal to d for simplicity. So I simply say it's a constant disturbance. Actually, it's a time varying disturbance. So if I do that, then from the final value theorem, this is the final value theorem, which says that limit s tending to 0, s of es is the error, which is here. Okay, that es. If I put it in there, s tending to 0, if I put s is equal to 0, so there is an s here, there is an s here, this will become 0. Okay, so limit s tending to 0, s of es, if I do that, then what was es? Es was equal to this, and in es, what do I put? I can put theta ds is theta d by s, and this ds is this one here. I put that in, put limit s tending to 0. So all the s's will become 0. This becomes 0. That will become 0. Okay, and there's an s there. So what is left is only this term. Okay, so it is. So in the omega also, the omega term, what does the omega term contain? So omega term has s equal to 0. It will become 0. It will cancel it out, right? So what we are left with is only we are only left with D. So what we are left with is D into R KKP. This is my error steady state. Okay, that is my error steady state. Now what does this mean? So this is an error steady state, means as time is going to infinity, this error will always be there. This error is never going to become 0. Okay, so which means that in a PD controller, this line will never go and meet that line. Okay, there will always be some error. How much error is there? This much error is there. Always, irrespective of what you do. Now, how can you reduce that error? Now, you can see that this error steady state, is directly proportional to D, the dynamic torque. And D is equal to M theta theta double dot plus V theta theta dot plus C theta. Okay, so the faster, and this dynamics is proportional to what? Okay, what does the dynamic torque depend on? This we have studied when we looked at dynamics. We saw that it depends on acceleration, it depends on inertia, it depends on Coriolis centrifugal, it depends on position. So if the manipulator is moving very fast, you'll have more error. If it's moving slowly, you'll have less error. Okay. Number 2 is the gear ratio is coming at the denominator, and there is a K into Kp. Kp is your gain. So ESS is proportional to D, that is 1, that is the dynamics, and it's inversely proportional to Kp, which means the proportional gain. So if you put a high proportional gain, what will happen is your error steady state will go down. Okay, but it can overshoot much more. That is something we'll see. So this is basically giving us an idea that irrespective of what you do, you are going to have some steady state error. And the steady state error is the one that is going to always be there as time goes to infinity. So in a PD controller, it is simple. So what is the moral of the story? So the moral of the story is that PD controller is stable, always stable, irrespective of values of Kp and Kd. They are positive, of course. So this is always stable. Okay, but the bad side of it is error steady state is equal to D by KKP into R, which means that error steady state is not equal to 0. It cannot become equal to 0. So you'll always have some error. But because there is a gear ratio sitting there, okay, in the denominator, if you have a very high gear ratio, your error will be very small. So this is also showing that the importance of the gear ratio in this full control structure, because the moment the gear ratio is very high, your error steady state will become small. If your proportional gain is high, again your error steady state is low. And if the manipulator is moving very slowly, then again what would happen is your error is less. Okay, so this is a very, very important equation in terms of PD control. Now let's look at performance of PD compensators. Now we can write it in general. We can write this equation. What was that equation? Let us go back and look at it. So this equation. Okay, this equation. Okay, we can write it effectively in terms of in this way, and we can write it in terms of s squared plus 2 omega into zeta s plus omega squared, and omega and zeta are called the natural frequency and the damping ratio. Okay, so we are writing it in terms of zeta and omega. Omega is then this determines the speed of response. Okay, so now we can write it in this form, and what we are getting is Kp is equal to omega squared J effective by K, and Kd is equal to this. So let me just go back and explain what we did here. So we have this equation. I want to write this equation in the form s squared plus zeta omega s plus omega squared. I want to write it in this form. Okay, so I have written it in this form. Yeah, so I have written it in this form. Now what is omega and zeta? So omega and zeta in terms of our Kp and Kd are given by this. So Kp is this, and now normally we put zeta equal to 1 so that the response is critically damped. So this is the damping ratio. Okay, so this is my damping ratio. So for critical damping ratio, zeta is equal to 1. Okay, so what we can do is we can put zeta equal to 1, choose the gains Kp and Kd such that zeta is equal to 1, and then what we can do is we can look at omega. What is the speed of response? Is it going very slowly? Is it going fast? Okay, so how is it behaving. So let's look at this very simple example. So let's look at this very simple example where we have this system in which, let's look at this example in which we have the characteristic polynomial given by, so let's look at this system actually. Let me just draw it so it becomes clearer. So this is my theta d, which is desired plus minus kp plus kd into s. This is a PD controller or compensator. There is a disturbance which is coming, so this is my d which is coming from here, okay, and this is my 1 by s squared plus s, and this is theta m. This is going back like that. So this is my system. This is two input system. This is one, and that's the other fellow, okay, and this is my robot link or the motor. Okay, now in this case, the characteristic polynomial, the closed loop characteristic polynomial is given by PS is equal to, so you can find out the characteristic polynomial, right? You know how to do that. So s squared plus 1 plus kd into s plus kp. Now assuming first that, assuming theta d, I want to go to the position equal to 10, and there is no disturbance. Let me say d is equal to 0, okay, and I also said zeta is equal to 1. So if you do that, then what we see is for different values of, so for theta d equal to 10, d is equal to 0. I'm saying d is equal to 0 now, there's no disturbance, and zeta equal to 1, critical damping. So this is my critical damping. So for different values of, kp and kd, what would the response look like? So if we just plot it, okay, we are just plotting the response. What we see is that this is my time axis, and this is my position 10, which I'm supposed to go, theta d equal to 10. Then we see that this is 0.2, 0.4, 0.6, like that. Okay, then we see that for omega is equal to 12, it goes like this, and it is here. Then omega equal to 8, it is here. Omega equal to 4, it is there. So for different values of kp and kd, so if I plot for different values of kp and kd, so omega equal to 4 kp is 16 and kd is 7. Kd is 7, and for omega equal to 12, which is the fastest, so this is omega equal to 12, my kp, your kp was 144, and your kd was equal to 23, and the other fellow was omega is equal to 8, and kp and kd is respectively 64 and 15. Okay, so this is basically showing you that if you change your gains, what happens to omega. So you can see here that the gain is very low, it's 16 and 7, whereas here the gain is very high, kp is 144. So you also see the response is very fast. Okay, now this is one case. The second case is if you put disturbance. Now if I consider disturbance on the system, suppose I see the next case. Let me change the color, the same thing, but I'm now considering the disturbance also. I'm saying disturbance d is equal to, just for example, let us say disturbance d is equal to 40. Okay, now if you plot, what you'll see is that this is the same. Now if you plot, what we'll see is this is my reference required, it needs to go there, this is my reference. So what you'll find that omega 12 is going like this and coming here, omega 8 is here, and omega 4 is here. Okay, so this is omega equal to 12, omega equal to 8, and omega equal to 4. kp kd values are same as here, kp kd is same as here. Okay, so you can really see that the moment you have added disturbance, what has happened is this fellow has come in now. Okay, and that is my error steady state, which is proportional to the dynamics d. Okay, so this basically shows us how do you design a control system. When you say PD controller, what does it actually do, or what does a PD controller actually mean? So what we are basically seeing is that when we say control a system design, it basically means I need to find what is this VK. Okay, so this is my controller. Okay, this is my controller, which is the VK. And if it's a PD controller, I'm going to design my PD controller, put it in here, then find what is the characteristic equation, look at the stability of the characteristic equation, and then look at the error steady state. Okay, that is the meaning of. So following exactly the same procedure, we talk about the design of a PID controller now. Okay, so PD and PID. Now in PID, what is done is you have proportional derivative and you have an integral gain also, Ki. So this is my Kp, Kd, and this is Ki. Okay. So I design my PD controller like this, and I put this fellow in here. Okay. I put it in there. Okay. And then I do exactly the same thing. Then what is it that we do? I take theta ds. Okay. And on the left hand side, on the right hand side, I have we are left with these terms. Okay. So basically what I do is this is my control system diagram for a PID controller. In the previous case, we had looked at a Kp and a Kd. Where is the control system diagram? It was yeah. So this is my control system diagram from Kp and Kd. So there is a Kp and a Kd here. This was my control system diagram. Okay, for a PD controller. For a PID controller, basically this is my control system diagram now. Okay, this is my control system diagram. Now, how do we input this? Let me follow the same. This is okay. The way we have to write it is Vs is equal to PD controller Vs, following exactly the same notations, Kp into theta ds minus theta ms minus Kd into S into theta ms. Okay, this was there for the PD controller. So let's have a look at the PD controller. What was there? So in the case of the PD controller, where is the PD controller? Yeah, so this is my PD controller. So from here only I'm adding one minus. So here I'm adding minus Ki, the integral gain, into ms. This part I'm adding for the I part. So that's P, that's D, that's I. Okay. So what I'm doing here is I'm adding minus Ki by S into theta ms. And then I'm doing exactly the same thing. So we are taking theta ms on the left hand side. Okay. And so I put this in this equation. Take theta ms on the left hand side. So on the right hand side, you'll be left only with theta ds, and you'll be left with this term. Okay. By R. And you'll be left with theta d will be there, and you'll be left with the dynamic torque dk by R. And your control system diagram is this one now. This is Kp is here, Kd is here. We are adding a Ki by S. Okay. Procedure is exactly same. Take Vs, put it inside here. Take theta ms on the left hand side. All the terms having theta ms. Okay, and so on the right side you'll be left with theta ds and dk, which is the dynamic torque. Then what we do is we find theta ms. Okay, and when we find theta ms, this omega 2 will come at the denominator, and omega 2 is now equal to j into s cubed plus this plus this. So now you see that this is a third order, s squared, this is s. Okay, now it is not possible to say whether the system is stable or unstable simply by looking at j and b and k. Now j, b, k, kd are all positive, okay, because they cannot be negative. But because it is third order, we cannot simply say, in this case we could say in ms squared plus bs plus k, we could say that this is always stable. In this case we don't know about the roots. Okay, so how do we find whether it's stable or not stable? We have to look at the Routh-Hurwitz criteria. Okay, I discussed about Routh criteria in the last class. Please look at the Routh criteria. How do we find? We have to first make the Routh table. Okay, so we make the Routh table, and so in the Routh table it will be s cubed, s squared, and then s. Okay, so it is going to be j effective. The next is going to be k, kp. Then the second term is going to be b effective plus kkd. Okay, that is this term. And the fourth term will be kki. So you need to find b1, b2. Okay, and how do you find that b1, b2 terms? You can find the b1, b2 terms by looking at, so b1 is going to become this minus of this into this minus that into that. Okay, s raised to 1, s raised to 0. Okay, so we need to find the b1 terms and the b2 terms. Please refer to the previous notes, previous class lecture. How do you find out? So b1 will become equal to minus of j effective into b2, into ki minus of kkp into b effective plus kkd, okay, divided by okay, this is what we get, what will be equal to b1, right? Now after we make the route table, we need to ensure that all terms of column are positive. Okay, that means all terms here have to be positive. Okay, and if you do that, we see that there is a j effective kki minus of this is coming, this term that I just wrote down here. Now for this to be positive, you have to ensure that ki is less than b effective plus kkd into kp divided by j effective. Okay, so this term here that I just wrote, this fellow has to be positive, it has to be greater than 0. Okay, so if you put this greater than 0, then what will happen is k will cancel, k and k will cancel. You will get that ki must be less than b effective plus kkd into kp by j effective. You need to satisfy this condition. Okay, this means ki is your integral gain. So in a PID controller, for this system to be stable, your integral gain has to be less than this term always, and if this condition is not satisfied, the system will become unstable. Okay, so this is something to note about a PD controller and a PID controller, that in a PID controller can become unstable if this condition is not satisfied. So PID can become unstable if this condition is not satisfied. Okay, so please note this, that it would appear that PID controller is better than PD controller always. Okay, but please note that PID controller can become unstable if this condition for Ki is not satisfied, whereas PD controller is always stable. Okay, so today we talked about the design of a PD controller and a PID controller, and we saw that when we write our full equation with the motor on the left hand side, and then with the input voltage on the right minus the disturbance torque, then we design the controllers, either a PD control or a PID controller, put it inside the input voltage, what we are giving to the system, then study the stability and see if the system is stable. Something to note very carefully is that PD control is always stable. Okay, and but the bad side is that there is always a steady state error, but that steady state error is very small. Okay, it can be made very small by increasing gear ratio, by increasing the proportional gain, whereas PID controller doesn't have any error, no error steady state, but it can become unstable if Ki is not properly chosen. Okay, so we'll stop today and we'll continue in the next class. Thank you.